Hello everyone, and welcome to the second video in our Class 9 series of lecture videos. At the end of our first video, I recommended that we revisit a general chemistry concept to help us understand how a 1.4 kcal per mole difference in activation energies for two competing pathways could lead to a 10-to-1 selectivity for one of those pathways over the other. So in 1887, Svante Arrhenius, a Swedish chemist, suggested that rate constants vary exponentially with inverse temperature. So the pertinent equation is some rate constant K equals some pre-exponential factor A naught times E to the power of negative EA over RT, where R is our gas constant, 1.9872 cals per mole Kelvin. You may be more familiar with the equation the natural log of K equals negative EA over RT plus the natural log of the pre-exponential factor A naught. So let's consider a reaction where we have a reactant B, which could either go to product A through a certain pathway or go to product C through a different pathway. Let's say that the rate of B going to A could be defined as K sub A, that's the rate constant. And let's say further that this is an irreversible reaction. So the rate constant of A falling back to B, K A minus, is negligible. Similarly, B goes to C with some rate constant K C. And let's pretend this is an irreversible reaction, so the rate at which C decomposes back to B, the rate constant Kc minus would be negligible. And so, just as we described, the rate of B going to A is simply the rate constant Ka times the concentration of B, as long as the reaction is irreversible, that is, Ka minus is very, very small to negligible, to zero. And similarly, the rate of B going to C is going to be the rate constant Kc times the concentration of B, as long as Kc minus is zero or very, very small. So essentially we've defined these as irreversible reactions. Here's an energy versus reaction coordinate diagram showing the potential pathways of B going to A or B going to C. Now, you may have noticed that A is thermodynamically more stable, that is lower in energy, than product C. But if your reaction is irreversible, then the speed at which it goes depends solely on the activation energies. And we can see that the activation energy for B going to C is smaller than the activation energy of B going to A. Of course, if the reactions are reversible, sometimes you can find the global minimum. So there are differences between thermodynamically and kinetically controlled reactions. For kinetics, we depend solely on activation energies, and for thermodynamically controlled reactions, we're dependent on the relative stabilities of the possible products. But for these possible pathways, we've already defined them as irreversible, so we're going to be kinetically controlled. So two equations we could write include the natural log of Ka equals negative Ea of A over RT plus natural log of A naught, and the natural log of Kc equals negative Ea of C over RT plus the natural log of A naught prime, assuming the pre-exponential factors for both of those pathways are the same. Then you could subtract the bottom equation from the top and you would get natural log of Ka minus natural log of Kc equals negative Ea of A over RT plus Ea of C over RT. According to our laws of logarithms, this reduces down to the natural log of the ratio of Ka over Kc equals equals Ea of C minus Ea of A divided by RT. And so Again, performing another tricky mathematical operation, we can go ahead and say raise each side of that equation to the power of e, and we get Ka over Kc equals e to the Ea of c minus Ea of a over RT. Now you can play with numbers and a calculator, and you can discover that if the activation energy for A is 1.4 kcals per mole greater than the activation energy for the pathway leading to C, your ratio of rate constants Ka to Kc is 1 to 10. This means your rate constant of Kc is 10 times greater than Ka, which means you produce product C at a rate 10 times greater than you produce product A, which means at the end of your reaction you have 10 times more C than A. So I hope this is intelligible. We could further, look at radical bromination in terms of the different types of radical carbons you could produce for a molecule. So for example, we already saw that abstracting a methyl hydrogen to produce a methyl radical and HBr, your change in enthalpy was about 18 kcals per mole. What's the difference between that and, say, abstracting a primary carbon hydrogen? Well, about 4 kcals, so it's only 14 kcals per mole to produce a primary carbon radical through radical bromination. How about abstracting a secondary carbon hydrogen in radical bromination? Well, you're looking at an activation energy of about 11.5 kcals per mole. And let's compare that to abstracting a tertiary carbon hydrogen. In that case, you are looking at 9.5 kcals per mole. So the take-home message from this talk is for radical bromination, it's going to be a highly selective process. So you are going to prefer to take tertiary carbon hydrogens from your molecule if they are available. You'll be very selective for brominating those tertiary carbons versus other types. Of course, the example we did was the radical bromination of propane. We found that we were 92% selective. We selected for the secondary carbon versus producing a primary carbon radical, and you can see there is quite a difference of 14 kcals per mole versus 11.5 kcals per mole. Of course, there are statistical considerations to add in terms of number of primary hydrogens versus secondary hydrogens, but this is still on the order of greater than 10 to 1, but maybe a little less than the 100 to 1. So I will see you for the next lecture video, where we'll discuss other types of halogenation selectivities that are observed.